A semaphore is a synchronization primitive that controls access to shared resources by multiple processes. It maintains a counter that represents the number of available resources. Think of it as a gatekeeper, ensuring that only a certain number of processes can enter a critical section at any given time. There are mainly two types of semaphores. The first is a binary semaphore, which can only have values of 0 or 1. It's like a simple lock, either locked, which is 0, or unlocked, which is 1. It is similar to a mutex lock and is used for mutual exclusion, where only one process can access a resource at a time. Here is a piece of code that shows how to initialize a binary semaphore. We are initializing the binary semaphore mutex to a value of 1, which means unlocked. This means only one process can enter the critical section at a time. The second type is a counting semaphore, which can have non-negative values. It is used to control access to resources with multiple instances, for example, if you have a pool of available connections. Here is an example of how to initialize a counting semaphore. We are initializing the counting semaphore resources to a value of 5. It means up to 5 processes can access the resource simultaneously. Semaphores have two fundamental operations: wait, also known as P or down, and signal, also known as V or up. The wait operation decrements the semaphore value. If the value becomes negative, the process is blocked and added to the semaphore's waiting queue. Here is an example of wait function. Notice how semaphore value decrements, and if the value is less than 0, process is blocked. The signal operation increments the semaphore value. If the value is not positive, a process is removed from the waiting queue and unblocked. Here is an example of signal function. Notice how semaphore value increments, and if the value is less than or equal to 0, process is unblocked. Semaphores are implemented at the operating system level to ensure proper synchronization. A semaphore data structure typically consists of a counter value, a queue of waiting processes, and support for atomic operations. Here is a sample code of semaphore data structure. The structure contains an integer value that represents the current count, a pointer to a queue that holds waiting processes, and potentially additional metadata. Semaphore operations must be atomic to prevent race conditions. This is achieved through hardware atomic instructions, disabling interrupts on a uniprocessor system, or using spin locks on a multiprocessor system. This is an example of using hardware atomic operations in the wait function. The atomic decrement function ensures that the decrement operation is performed without interruption, preventing race conditions. Binary semaphores can be used to ensure that only one process at a time can access a critical section, preventing race conditions and ensuring data integrity. The binary semaphore acts as a mutex, allowing only one process to hold the lock at a time. Here's how to achieve mutual exclusion using binary semaphores. First, we initialize a binary semaphore to a value of 1, indicating that the critical section is initially available. Before entering the critical section, the process calls the wait function, which decrements the semaphore value. If another process is already in the critical section, the semaphore value will be 0, and the current process will block until the semaphore becomes available. After exiting the critical section, the process calls the signal function, which increments the semaphore value, allowing another waiting process to enter the critical section. The producer-consumer problem involves processes sharing a fixed-size buffer. Producers add data to the buffer, while consumers remove data. Semaphores ensure that producers don't add to a full buffer and consumers don't remove from an empty buffer, preventing buffer overflow or underflow. In this scenario, we use 3 semaphores: empty, which counts empty buffer slots and is initially set to the buffer size; full, which counts filled buffer slots and is initially set to 0; and mutex, which is a binary semaphore for mutual exclusion and is initially set to 1. Here is an example of semaphore initialization and the definition of the buffer, along with in and out indices to manage the buffer. Let's examine the implementation of the producer-consumer problem. The producer process produces an item, waits if the buffer is full by calling wait on the empty semaphore, enters the critical section by calling wait on the mutex semaphore, adds the item to the buffer, updates the index, exits the critical section by calling signal on the mutex semaphore, and signals that an item is available by calling signal on the full semaphore. The consumer process waits if the buffer is empty by calling wait on the full semaphore, enters the critical section by calling wait on the mutex semaphore, removes an item from the buffer, updates the out index, exits the critical section by calling signal on the mutex semaphore, signals that space is available by calling signal on the empty semaphore, and consumes the item. The readers-writers problem involves processes that either read or write to a shared resource. Multiple readers can access the resource simultaneously, but writers need exclusive access. Semaphores help coordinate this access to prevent data inconsistency. In this problem, we use two semaphores: mutex, which protects access to the read count variable and is initially set to 1, and WRT, which controls write access to the shared resource and is also initially set to 1. Additionally, we maintain a read count variable to track the number of readers currently accessing the resource. This solution gives readers priority over writers, which means writers may starve if there is a continuous stream of readers. Now, let's look at the implementation of the readers-writers problem. The reader process waits on the mutex semaphore to access the read count, increments the read count, and if it is the first reader, it waits on the WRT semaphore to block writers. It then signals the mutex semaphore, performs the reading, waits on the mutex semaphore again, decrements the read count, and if it is the last reader, it signals the WRT semaphore to allow writers. Finally, it signals the mutex semaphore. The writer process waits on the WRT semaphore, performs the writing, and then signals the WRT semaphore. It's important to note that this implementation gives readers priority over writers, potentially leading to writer starvation if there's a continuous stream of readers. Let us explore the dining philosophers problem. 5 philosophers sit at a round table with 5 forks. Each philosopher alternates between thinking and eating. To eat, a philosopher needs both the fork on their left and right. The challenge is to design a solution that avoids deadlock and starvation. One solution involves using one semaphore per fork, which represents a resource. To prevent deadlock, symmetry is broken by allowing only 4 philosophers at the table, making them pick forks in a specific order, or using an additional room semaphore. It is ensured that no philosopher can starve. In the code example, a semaphore array called fork is initialized with 5 semaphores, each with a value of 1, representing the availability of each fork. A semaphore called room is initialized with a value of 4, allowing only 4 philosophers to enter the dining room at once. Each philosopher waits to enter the room, picks up the left fork, picks up the right fork, eats, puts down the left fork, puts down the right fork, and leaves the room. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.